Now we can address how filters respond to harmonic inputs. But first, a little bit of background of why are we interested in filters. Now, when we're measuring a signal, all signals are going to contain some undesirable noise in them. So let's say we're trying to measure the position of our object, and it's a nice sinusoid that we're trying to measure. Well, the voltage reading that's going to come out is not going to look like a perfect sinusoid because the real signal is going to contain a number of frequencies. It's not only going to contain the one we're trying to find, which is the actual position of the object. So for example, if our sensor is plugged into the wall, we're going to get 60 hertz line noise. So we're going to see some 60 hertz signal happening in what we're reading. If we have loose connections, especially if we have a moving object, then we're going to see that as the wires move, that's also going to introduce some extra signals that we're going to be reading. And all of these are not the thing we're actually trying to measure. They're these extraneous noise that ideally we would like to get rid of so that we are able to calculate what's the actual position of our object and not what's the position and all of this other stuff going on. So hopefully this extra stuff, this noise, is going to be happening at frequencies that our object is not experiencing. So if we have some slow moving object that we're trying to measure its position, let's say much less than 60 hertz, but we have this noise happening at 60 hertz, maybe something else that's even more high frequency, well, we know our object is not actually vibrating at that 60 hertz or let's say 100 hertz. So what we can do is we can filter that out, filter out these artifacts, these things that are kind of false in the signal that we are collecting. And that's what a filter's job is going to do. So typically what we want to do when we're choosing a filter or designing our filter is we're going to choose a cutoff frequency. So let's say we're talking about this low speed position that we're trying to measure, this low frequency position we're trying to measure. We would probably want to have a low pass filter. Low pass meaning we're going to pass through unchanged low frequency things, and we're going to hopefully get rid of higher frequency things. But the idea of the cutoff frequency is that kind of on one side of the cutoff frequency we're going to keep stuff, and on the other side we're going to try to get rid of it. So we want to choose a cutoff frequency such that it's high enough that we're going to keep the things we're interested in, but low enough also that we're not going to keep a lot of stuff we're not interested in. So the cutoff frequency technically is where we are going to be reducing our magnitude to the root 2 over 2. And we'll see in our example what that exactly looks like. Now, because we're dealing with real filters and not an ideal filter, a filter is going to have what we call roll-off. So there's going to be a segment where we are going to be getting rid of some of the noise that we're not interested in, but we're not able to get the amplitude of the noise all the way down to 0. We're going to be able to reduce it, but it's still going to be a little bit present in the signal that we're keeping. And then everything before that roll-off is going to be kept as is. Right, so I just mentioned a low pass filter. That's often what we will be interested in maybe a mechanical system. But 4 basic types of filters that we can deal with. Low pass, like I explained, it passes through low frequency signals and is going to get rid of higher frequency signals. A high pass filter is going to do the opposite. Above the cutoff frequency, we're going to be keeping unchanged those signals, and then below the cutoff frequency, we're going to be trying to get rid of those. We can have a band pass filter, where actually we would choose 2 cutoff frequencies. Basically a band pass is like a low pass and a high pass put together. We want to get rid of very low frequencies and very high frequencies and keep things in the middle. And then we can have a notch filter, which is going to get rid of frequencies at like a very specific tight range. So for example, if we have that 60 hertz line noise, well, if our object is not moving at 60 hertz, we might want to put in a notch filter at 60 hertz to get rid of that noise because we know it's going to be happening at 60 hertz. Now, a problem we're going to see when we have filters is the good part is we can get rid of this undesirable part of our signal that's going to be kind of muddying up what we're trying to be measuring. But depending on the filter that we're going to be using, a filter can introduce lag into our output signal that would not have otherwise been there. So especially as we get up to harsher filters or higher order filters, the thing we're measuring is going to be, again, delayed from the quantity, the value of the quantity that we're actually measuring as it passes through our filter. So as we're looking at the Bode diagrams for the filters, we just want to be aware of that the signal that we're trying to keep might have this time delay.